lot of us take generic drugs, and many people have misconception of the chemistry that goes on in the generic area, or is catalysis important in the generic area? And my point is very important, and it's more important in the generic business than it is in the innovator chemical industry, where the drugs come from. So without any further ado, let me get started. So I wrote several chapters on books, and these are the books. And if you are interested, you can get a hold of them, and you can read about the generic business and the compounds that we developed in Dr. Reddy's. Now, why is green chemistry important? Of course, we all know why green chemistry is important, so I don't want to dwell too much on that, but it is important because the design, manufacture, and use of chemicals and processes that have little or no pollution potential or environmental risk. And the most important part, they have to be both economically and technologically feasible. If there is no economic gain, then nobody will practice that chemistry. So now the question is, why green chemistry? Well, the one word is sustainability. How do you define sustainability? Sustainable development meets the needs of the present without compromising the future. So we need to balance the present and the future, both, because of sustainability. And the most important sustainability that I'm going to be discussing is the environmental and ecological sustainability. But there is resource sustainability, economic sustainability, and social sustainability. But the two most important parts are the economic and environmental, and they are related. Just because you are trying to help the environment, but if it's not economically feasible, it's not going to go anywhere. So when you think about it, only 10% of the resources removed from the earth end up in the goods manufactured. That means the computer screen that you are sitting in front of and everything else, only 10% of that, which came from earth, we are using, and this 90% is landing up as waste. So, and that is not a sustainable situation, because the waste keeps going up and up, and the resources going down and down. And in the pharmaceutical industry, it's even worse. So at last we met the enemy, and it is us, the famous quote. And there are some numbers that are mind-boggling. For example, even research has shown that producing a standard PC and monitor takes 240 kilo of fossil fuels, 20 kilo of chemicals, and 1,500 kilo of water. That is just an astounding number. And it doesn't matter whether it's a computer screen or it's an iPhone, the numbers are the same. So it's not a sustainable situation, because we change phones or computers every 3 or 4 years. So production cost for a typical specialty chemical, material 25%, energy 13%, labor 13%, capital depreciation 13%, and waste 36%. That's the production cost. So most of the cost comes from waste. And this is the old number, 1994 reporting year. There are 2.6 billion pounds of approximately 300 hazardous substance released to the environment. At this rate, the time it would take you to read this, over 1 ton of hazardous waste will have been released. So now this is, of course, a lot more. An average car produces 22 kilo of carbon dioxide per 100 kilometers. And it takes 80 trees to absorb the carbon dioxide that an individual breathes out in one lifetime. And we don't plant 80 trees to replace us. So we see an endangered species every time we look in the mirror, and it's not about the whales or penguins, it's about us, it's about you and I. And the question is, can we do better and leave the world a better place for our next generation, for our children and our grandchildren? Now, the waste, of course, is very costly, cost of manufacturing, transportation, storage, processing, purification, recycling. There are incidents that happen that are PR disasters. Supply chain, which is very, very important today than ever before, because we have a big supply chain disruption during COVID. Financial perspective and the cost of meeting regulations, which are constantly going up in a hockey stick curve. So this is the regulation curve, typical regulation curve, that looks like almost like a hockey stick, because it's going up very sharply. So the genetic dilemma, rapid growth in the genetic business, it's growing so quickly that it is almost uncontrollable growth. And there is a good article in the CNN News that I have in September 29, 2014 about the growth. And you can see that from 1984 to 2013, how the genetic business has expanded. And these are the prescription for genetics. They have gone up and up and up very, very quickly. So growth in the genetic business, sale per $1 billion, 2006 to 2020, sale is steadily going up. And that's a good thing for market because market needs to go up in order to invest in any kind of business. So anytime some compound goes generic, for example, when a drug goes generic, in this case, the Zocor, which is simvastatin that was made by Merck. When Merck made simvastatin, this was the entire market in 2005. In 2006, it went off patent and Merck lost its share. And 2007, it's gone. So most of the genetic business takes over when the drug goes off patent. And Dr. Reddy's kept a small share, first to file and obtain 180 days of market exclusively. So when you do a para 4 challenge, which means you come to the market a year before the drug goes off patent, then you can take over the market even 1 year before. And once the doctor starts prescribing it, they will not change their prescription. So rapid growth, the FDA approvals, and they are the numbers for both genetic drugs and new drug application and biologics and licenses. And biologics and licenses are not going up that much because it takes longer time to develop biologics and licenses. But still, they're very steadily going up, all the genetic drugs, the ANDA, or abbreviated new drug application. Genetic companies have become more aggressive in challenging innovative drug patents. To compete, they are expanding geographically and building portfolios. And as the pharmaceutical industry on which they rely undergoes its own changes, genetic companies are finding new products to imitate, including a new generation of biologics. So let me just quickly go over one example and show you what I'm talking about in a genetic business. This is the first product that we handled when I came to Dr. Reddy's, and we had to make 15 tons of rabiprazole that we made for Teva. And this is a very simple synthesis, 3-step synthesis. You alkylate with a sulfur and you make a sulfur carbon bond, kick out the bromide, and then you oxidize the sulfur to sulfoxide, and then you simply make a salt with sodium hydroxide. So this is a 3-step straightforward synthesis, especially the last step, which is actually a no reaction step, right? Well, till you see the first step, and these are the unit operations for the first step. Each unit operation takes place in one building, essentially. So essentially, there are so many unit operations just in the first step. And then the second step is, again, so many unit operations, and each unit operation costs time and money, but it's not just one step. And the simplest of them all, the last no reaction step, is this. So when you are purifying the final product, the API. So all these unit operations, so when you look at a 3-step synthesis, it's really deceiving to see that how not so simple it is. And these are all putting pressure on the environment, and the green chemistry application is much more important from the genetic standpoint than from the innovator standpoint, because genetic companies have to make drugs even purer than innovator companies, because there is no patent protection, so the FDA requires stringent requirement for genetic companies. So the purification steps are more, boxes are more. This is the major solvent consumption: acetone, ethyl acetate, chloroform, DMSO, MTP, methanol. These are all tons per kilo. Per kilo, this much. Water, 300,000 per ton. So that's distilled water. So that's a lot of energy that goes into making distilled water. So when you look at the synthesis, it's mind-boggling how much waste that we are producing per kilo of product. So reverse engineering is another way genetic companies works. For example, you look at a valsartan synthesis where you make the amide bond in the last step, and the direct amide bond formation is protected. So you cannot make this bond directly by any kind of standard chemistry because it's all protected by patent. So one way to do reverse engineering is put a protecting group on the substrate, and that goes around the patent, and then you make the amide bond, and then you take the group X group off. Well, it is non-infringing technology and reverse engineering, and it looks pretty simple till you practice this chemistry. And when you are making the amide bond, you are activating the carboxylic acid, and that is patented. But when you use, let's say, chloro and then convert it to a sulfur and then reduce the sulfur back to carbon, the carbon-hydrogen bond, the sulfur attacks the activated acid and make a six-membered ring. So the overall yield is 40%, even though you can practice it. So even genetic companies will make, when the compound is going to off patent the first year, they will make it this way and challenge for para 4, but the yield is really, really poor. But because they don't have to, because the genetic companies are cheaper to operate, they can still make the drug, but it puts a lot of pressure on the environment. So it's not infringing, but far from being cost effective, involves cumbersome protection, reproduction, low yielding, and definitely not green. So waste generation, how do you use the waste generation or measure the greenness of a compound? Well, you use kilo per kilo product. So waste, you measure the waste per kilo of product. And you see oil refining industry is 0.1. So there is no waste in oil refining. Why? Because everything that makes in oil refining goes into, get used up. But as you start to bulk chemicals like methanol, acetic acid, then you start making more waste, but it's still not much. But then you come to fine chemicals, paints and plastics, then you start seeing the waste 50 kilo per kilo of product. And then in pharmaceuticals, 100 kilo per kilo of products. So 99.9% is waste and 0.1% is the product that goes into our body. So is it half full or half empty? It's pretty scary actually. With 100 plus API, some of it is as many as 10 to 15 steps, notwithstanding the one that is already in the pipeline and the one that will enter the pipeline, it looks pretty gloom. We are facing a formidable challenge. It is also a unique opportunity. So it is either half empty or 3/4 full, because there is a significant opportunity for all of us to overcome this difficulty and solve these problems in a meaningful way and make the world a better place. So there are 12 principles of green chemistry, and I'm sure most of you are familiar with it. And this was formulated by Paul Anastas and John Warner, is a good friend of mine, both of them. And we served in national academies together. And these are the most important principle is the prevention. In other words, if you don't make any waste, you don't have to worry about all this. But then Barry Trost has this concept of atom economy. So all the atom needs to be utilized. Hazard is important, less hazardous chemicals, designing safer chemicals, safer solvents, energy, renewable feedstocks. So if you can use sugar instead of benzene, that's better. Reduce derivatization or don't protection, deprotection involves more steps. Catalysis is very, very important. Design for degradation and real-time analysis, which is important from FDA point of view. Before the drug was developed and it was made by 3 batches with varying conditions. Today, FDA want real-time analysis and following the reactions. So inherently safer chemicals. So environmental impact of solvent. Solvent are the biggest culprit. Solvent reduction starts with understanding its fundamental role, solubilizing reactants, controlling reaction rates, heat, mass transfer. So solvents you need, but solvents are the biggest culprit. As you saw, most of the waste comes from solvent. In any API synthesis, this is a general graph where solvents occupy most of the space as opposed to the product and the reactants and others. So solvents are really the biggest culprit in the reactions. Now, green process research is what we try to practice. And what is green process research means you have to make the process green that makes money. So an ideal process can be defined as a process where the target is made from readily available starting materials in one simple, safe, environmentally acceptable and resource effective operation that proceeds quickly and in quantitative yield. So that's the definition. Well, or even better, a simpler definition, the ideal chemical process that is that which a one-armed operator can perform by pouring the reactants into a bathtub and collecting pure product from the drain hole. This is a very simple definition by Sir John Cranforth, who got Nobel Prize in chemistry. So I'm going to now discuss some of the things that we have learned in universities and in educational system, and I'm going to challenge those concepts in terms of green chemistry and industry. Now, when we say as a chemist, what is our job? Or an engineer, what is our job? Maximizing overall yield and reduce the number of steps. But their usefulness are limited. Why is that? Well, as Voltaire said, that before you can start argument, you need to define your terms. So let's ask, what is a chemical step? How do you define a step? Well, a chemical step is represented by an arrow in which a synthetic scheme, as long as there is a space to pile up reagents. So A to B, I'm starting with A, I'm pile up B, and I'm saying that's a step 1. And then B to C is step 2. So that's how we measure steps. And we say this is a 2-step synthesis. But as I showed you, that 2-step synthesis can be more complicated than it looks like. So the truth is, a chemical step should equate to a number of unit operations, those boxes that I showed you, distillations, filtrations, crystallizations, drying, etc., in a synthetic sequence. So a step is not a step, it's a combination of unit operations, and we don't define a step by unit operations. But don't forget, this practice will sacrifice additional control. If you eliminate one unit operation, it puts pressure on the other unit operations to improve the quality. So these two factors should be balanced prudently. So if you want to minimize unit operations, you have to have the other unit operation steps better so that the pressure can be balanced in the sequence. Chemical yield. Well, we always calculate chemical yield in our classroom, and we teach our students how to calculate chemical yield. Well, how do you define chemical yield? For example, let's take a linear route, 8-step synthesis. So this is a linear route with 8 steps. Now let's take a convergent route, and we always tell our students the convergent route is better. So this is a convergent route with different routes that are combining together to make the product. So A and B is combining, C and D is combining to E, and these are the steps to make the product. And that's also 8 steps. So are the schemes in the convergent route twice as efficient as that in the linear route, because its longest linear sequence is only 4 steps? So if you look at the longest linear sequence, 1, 2, 3, 4, that's the longest step. So you say this is the step that goes to the product, then it's 4-step synthesis. So is it better because it's 4 steps? Or are both schemes the same since they have the same number of total steps? So how do we define what is better becomes a little bit murky. Now linear versus convergent, let's compare head to head. A linear route is 8 steps, convergent route is also 8 steps. Now, what is the overall yield in the linear route? Now, if you assume 90% yield at each steps, the overall yield is 43%, 0.9 times 8 to the power 8 for the linear route. Now, what is the overall yield in the convergent process? Well, is it 66%, steps 5, 6, 7, and 8, as the cumulative yield of the longest linear sequence as commonly practiced? So we take the longest linear sequence and we define these are key starting material. And based on that, it will be 66%. Or is it 73%? Because A is the designated starting material, since it contributes majority of the molecular weight or complexity. So let's say we are making a steroid, we start with the steroid, and we start functionalizing the steroid along the route. So we say this is the process, and these are the functionalization steps. So now the yield goes up to 73% if we decide this is the route. So it's not so simple when you calculate yield. So convergent, and the truth is convergent synthesis have many intrinsic merits. A highest overall yield is not one of them, but that's not how we learn in an education system about yield. Overall yield in a convergent synthesis invokes picking a linear fragment of a whole picture and ignores the rest, and that is wrong. The number of steps is not an objective measure of efficiency. So when you say number of steps are less, this is a better synthesis, that's not objective. And overall yield and total number of steps are only two among many criteria that must be considered. Now let's look at logistics. When you look at a synthesis, we always look at the logic, but there is another part, which is logistics, which also come into the picture. And that is the least understood and most underappreciated factor in the whole equation. Convergent and linear routes. A convergent route is least perturbed by process variation because the alignment of the steps disperse risk evenly. So you are coming from different routes, so they are more balanced, and it's least perturbed because if one step goes down, there are other steps that can make up for that perturbance. A convergent route requires shorter cycle time, a higher throughput with parallel processing. You can do everything parallel. So you don't have to wait, the operators don't have to wait for the compound to be made in step 2, step 3, step 4, essentially, in a linear route. So a convergent route, you can work parallelly. In a linear route, more fragments ride along non-productively than non-convergent. So every time in a linear route, you're running a step, you're losing 10%. So 10% of the soldiers are dying in the field. So they are riding along so unproductively. So in step 9 or step 8, you are killing a whole bunch of soldiers which started from step 1. The impurities, it's very important, generated by a convergent route tend to be less similar than those from a linear synthesis. From a linear synthesis, impurities are very similar, but in a convergent route, they're very dissimilar. So you can crystallize and purify because they don't look like each other. So purification is easier in a convergent route than in a linear route. So workup is less and it should be greener because you generate less waste. Now, space-time yield throughput, unit time productivity for a given manufacturing process is dictated by vessel productivity. It is the major factor governing conversion cost. So when you calculate yield, you have to calculate space-time yield, part-time per vessel productivity. So logistics in quality and impurity rejection. A lot of times when you make products, you have to make it 99.9% pure. So we tell our supplier that, you know what, I need 99% pure material. And the supplier says, I cannot make 99% because it's going to cost you more because I have to crystallize it. Every time you crystallize, let's say this is your starting material, X is the impurity. When you crystallize X to get 99%, you have to do 1, 2, or 3 crystallization. And every time you crystallize, you lose part of your A, more A than X because there is more A is present than X in the mother liquor. So your chemical yield of the starting material goes down, your cost goes up. Now, this is called purification or reaction control. It takes advantage of the fundamental law of mass action and differential reactivity of the substrate. Let's say instead of buying 99% pure material, you order 90% pure material, which is much cheaper. And then you run the first step. Well, what does law of mass action tells you? That the thing that is 90% or 10-to-1 ratio, it has its own order. It will react 10 times faster than the one that is present in 10%. So this, if it reacts 10 times faster, 90-10 will automatically become 99-to-1 because this is a bimolecular reaction. So just by running the reaction, you can purify the material by using law of mass action. And the second step, 99 will go to 99.9% to 0.1%. So a lot of time we make a decision based on economics that get pure material, we don't have to worry about purity in the last step. Well, but think about the cost. You don't need to get pure material. Law of mass action and bimolecular reactivity, the higher the material, the higher the amount, faster is the reaction. It will automatically clean it up as you are running the reaction. So reaction control is important. Now, logistic placement of a low yielding step. Where do you put a low yielding step? There is no good place for a low yielding step anyway. But these are, I'm talking about logistics. Inefficient steps should be placed earlier in the sequence. Overall yield remains the same. So overall yield doesn't change where you put the low yielding step. Let's consider chiral resolution, 50% yield in an 8-step sequence. So you are resolving a chiral material and you are throwing away the wrong enantiomer. So it's a 50% yield reaction. In an 8-step sequence, doesn't matter where you do the 50% yield loss, overall yield doesn't change, but the cost changes significantly. In an 8-step sequence, the cost increases by 100% if it's done in step 8. So you bring the last step and you throw away 50%, your cost is 100% higher. 13% in step 1 and 23% in step 2. So where you put the low yielding step in a synthetic sequence is very important. This is not chemistry, this is logistics. And a chemist need to understand logistics to develop a process. So the focus on development efforts, the impact of improving a step. A lot of times we try to improve the step and 10-step synthesis. Which step should we work on? The impact of improving a step yield is different depending on which step is being optimized. Overall yield remains the same no matter which step is optimized. So overall yield doesn't change. An improvement in yield from 90 to 95% for step 8 in an 8-step synthesis lowers the overall cost by more than 5%, while the same yield increase for step 1 has almost negligible effect. So simply because you want to improve the yield, and that's very important in genetic business because cost is the key, because the profit margin is very, very small. Total profit is high, but profit margin is small. So you need to be very careful. How do you put your effort and where do you develop your process? Which step? Placement of a dilute step. Where do you put the most dilute reaction? High dilution should be avoided at all costs. A high dilution step should be placed towards the end of the synthesis. Smaller amount of material requires less solvent. Solvent usage is high if the dilute step is placed in the middle. For the first few steps, substrates have low molecular weight, but requires higher mole quantities. You are now using number of moles, but low molecular weight. But for later steps, substrates have higher molecular weight, but lower mole quantities. So this is where the diluent step, where you put it, is important. Safety is, of course, very important. Avoid accumulation of unstable or energetic intermediates. Highly exothermic unit operations can be carried out safely through the sound engineering and additional rate control heat management. The explosion hazard needs to be evaluated by calorimetry. Quality by design is the most important thing that FDA pushes today, is that you have to follow the reaction essentially. So analytical control is very important. Minimizing the introduction and generation of impurities. Perfecting analytical methods for their detection and establishing procedures such as crystallization for their removal, and quality by design is the mantra for FDA today for developing generic business. Now, durability and robustness. How do you define a process durable? Well, robustness refers to the reproducibility despite variations in process parameters. Is it reproducible? And durability measures the robustness of the entire process along its projected useful lifetime or life cycle. So durability has the following key features. Starting material have multiple synthetic sources, and this is very important today after a post-COVID world, where even though you have 3 sources, let's say, but the first 2 sources get their starting material from source number 3. So it doesn't matter if there are 3 different sources. If the source number 3 is making starting material for all 3 of them, then you have 1 source. So you have to have diversified source. Otherwise, it will happen like it happened last year. Suddenly we ran out of penicillin because everything is outsourced to 1 place, 1 city in 1 country. Green process. It has to be a green process. Can be easily scaled up or down. It is capable of incorporating advances in science. If there is a new way to do a new step, you should be able to incorporate quickly. Flexible. And in the process will remain as the route of choice as long as the product is in the market. So that's the durability or robustness of a process. Process intensification and flow chemistry. So this is the engineering part of green chemistry that is incorporated into chemistry. So definition at the process, what is process intensification? That means a set of often radically innovative principles, a paradigm shift in process and equipment design. So you can take a batch process and make it continuous in all these different reactors, spinning tube reactors, microreactor, compact heat exchange, and you don't need a big plant. All you need is you can do it in your garage with pumps. So spinning this reactor looks like this, and we have used all of them in our genetic business. This is a spinning this reactor where the surface area is so high, reaction is over very, very quickly. This is a microreactor. You can scale up a whole reaction to make ciprofloxacin just in 1 microreactor in essentially in 1 room with pumps and microreactors. So these are rotating packed bed reactors. These are all different equipments for continuous processing. Spinning tube in a tube reactor where the tube rotates inside a tube and the surface area goes up and the reaction goes faster. So now history of chemical manufacturing, nothing has changed in last 500 years. It's still batch to batch to batch, except the batch looks more scientific. So batch manufacturing, there is a risk, large capital requirement, changing dynamics and safety. So the main aim of the research was to decrease speed and to get control. For example, you were doing a lithium exchange from lithium to magnesium to zinc to tin, the reactivity goes down. And decreasing reactivity means better control. So when you're doing a lithium reaction, it's such a fast reaction because of the high heat and mass transfer rates in continuous tubular reactor. The reactions in a continuous tubular reactor can be done at a high temperature. You don't have to cool it down to -78. So continuous processing becomes important when you have to have reaction where they are so fast that you have to cool it down to -70 or -80 degrees. So speed versus control, but why not speed with control? And this is where continuous flow processes comes in. So this is the kinetics for the batch process is in the minutes or hours, and kinetics for the continuous process is in milliseconds or microseconds. And eventually we are reaching up to picoseconds and femtoseconds, very, very quick. So history of chemical manufacturing. So these are some of the literature on flow chemistry. And flow chemistry falls in between chemists and engineer. And if the chemist knows engineering or the engineers not chemist, you can be a better chemist or engineer or both. So there is no one solution for everything, but there is a solution for almost everything. Batch versus flow. And what is the most important part in a flow? In a batch reactor, the starting material goes down and the product goes up, but the product is in the same environment as the reaction. So most of the time, the reaction is the reaction is in the vicinity of the product. So it starts decomposing because you are still reacting. But in a continuous flow reactor, it comes in very quickly. So as soon as it comes out of the flow reactor, it's out. So the length and time, the adjusting length and time, each molecule passing through the device experimenting the same reaction times, excellent batch-to-batch producibility, no headspace, no secondary nucleation, scaled up without the optimization. And if, for example, in electrophilic substitution, you get an ortho-para ratio. But if you in a batch reactor, the para is pumped first and then it goes to the ortho. But here, the para is pumped first and it's out of the reaction sphere, so you don't get any ortho. So there is a significant advantage and selectivity increase in a continuous flow. And this is a simple chart of continuous flow where if a reaction at 20 degrees centigrade takes 1 hour, it will be 15 minutes at 40, 4 minutes at 60, and 56 seconds at 80. So you can run the reaction in a continuous reactor very quickly with 56 seconds residence time. And this is the selectivity. You have two processes with different reactivation, and the continuous processes has very sharp selectivity. So you get a higher selectivity in a continuous, but in a batch reactor, it's broad. So the selectivity goes down significantly. And when you do continuous processing, for example, in a screw cup vial, the pressure rating is 10 bar. But in a stainless steel tubing, you can do 100 bar because you can do reaction at a very high pressure. So this is the Timothy Jamison synthesis in MIT for ibuprofen is pushing the boundaries. In a total residence time of 3 minutes, ibuprofen was assembled from its elementary building blocks with an average yield of about 90% in each step. So very, very quickly. So it can replace batch manufacturing in a very quickly. And this is the ultimate for continuous process, which was done by MIT and Novartis for aliskiren, all the way from starting material, long step, to tablets, to final product, formulation products. And this is the plant. It looks essentially, I visited that plant, and it's almost like a train compartment. It's no bigger than a train compartment. And you are making everything all the way to the tablet. So let's environmental impact and understanding each step at a fundamental level. Amide formation. Let's look at amide formation, which is quite atom economic. You have a carboxylic acid, you have an amine, and you eliminate water, dehydrate to make the amide. It looks atom economic, right? But wait till you calculate the molecular weight of the coupling agents. And these are the coupling agents that are used for amide formation. This activates the carboxylic acid. This activates the carboxylic acid, make the OH a good living group. Nitrogen comes in, kicks out the OH. And this is the byproduct dicyclourea. By far, this is not green. And the molecular weight of all this is a lot higher than the amide. So this is not atom economic. This is a good process for making the byproduct dicyclourea, not the product. So is it possible to achieve a green amide synthesis? Well, let's ask. What are the essential ingredients we need to make an amide? Well, we need a carboxylic acid, we need an amine, and we need an activating agent that will activate the carboxylic acid OH to make it a better living group that can be kicked out with the nitrogen. So what would the process look like? The activating agent will activate the oxygen of the OH and it will make it a better living group. Nitrogen is going to come and kick out the living group. So the problem is the activating agent being acidic flirts with the amine and deactivates the amine because it's acidic. Instead of flirting with the oxygen, it flirts with the nitrogen because it's more basic and kills the amine. So there is no reaction. So that's the problem. So how do you solve this problem? Well, the trick to a successful amide synthesis will be to find an activating agent that will form a happy activation complex that will not likely to flirt with the amine, maybe a weak acid instead of a strong acid. So it will be weaker and it is used in catalytic amount. So at a given time, there will be finite amount of amine left. So if you use less amount, catalytic amount, there is amine left to react. So it's not deactivated. And the answer is boric acid. Boric acid is a weak acid, pK 9.7. When you combine with carboxylic acid, it makes a happy complex, hydrogen bonded. And that happy complex now can be kicked out. So a green synthesis of amide looks like this. Carboxylic acid reacts with boric acid to make the borate complex. Nitrogen comes in, keeps out the boric acid. It's catalytic. Water is the only byproduct. It's simple, elegant, and it's cost effective. No wonder it is green. Well, a green synthesis of amide, does it work? And we made several amides API by this method. So environmental impact means understanding each step at a fundamental level. When the reaction is complete, add more reagent. That's what we have been taught in high school, in college, in universities. Reaction is not going, add more reagent. Is this conventional wisdom or another wasteful practice? So I'm going to talk about solidification synthesis, which is this guy here. You add the quinacridinol with sodium hydride, that deprotonates the OH to make O-, that kicks out the ethoxide to make solifenacin. And the overall yield is 50%. There is unreacted starting material, and byproduct is this. Well, low yield, this is wasteful, unreacted starting material, complicated separation, purification, solvent usage, use of large excess of expensive reagent, quinacridinol, and use of large excess of sodium hydride and safety concern. So definitely not green. This is not a good process. So let's ask, what's the sodium hydride doing there? Well, sodium hydride is deprotonating the OH to make O-. Great, and the O- is now coming in and kicking out the ethoxide to make solifenacin. But all is not well. There is a serious problem. Sodium hydride and water don't like each other. So sodium hydride is moisture sensitive. It reacts with water to make sodium hydroxide. So sodium hydride will react with water, deprotonate the water to make OH-. Sodium hydroxide is small, sneaky, and dangerous. So instead of quinic alkoxide base, the hydroxide is now coming and kicking out ethoxide, and we get the COOH that eliminates carbon dioxide to give you this guy back and starting material back. So we need at least 1 mole of sodium hydride to make 1 mole of alkoxide. We need the sodium hydride to make alkoxide, or do we? Well, let's look at it more closely. Sodium hydride deprotonating alkoxide. The alkoxide is making ethoxide. So for every mole, you're making 1 mole. For every molecule of solifenacin being formed, 1 molecule of ethoxide is being regenerated simultaneously. And ethoxide is a strong base, just like sodium hydride. So ethoxide is basic, just like sodium hydride, and can do the same thing as sodium hydride. So with the base is being regenerated, it is recycled, and the entire process can be essentially catalytic with respect to the base, sodium hydride. So we don't have to use a mole of sodium hydride or excess sodium hydride, use catalytic sodium hydride by understanding the reaction from first principle. So this is the catalytic solifenacin synthesis. Yield went from 50 to 87%. So how much time do I have? I have 6:39, 40 minutes talk, right? This is 40 minutes,
doctor,
right?
You're having more 5 minutes, that's it. More 5 minutes.
Okay. Okay. So this is green. So greenest process is always going to be the most cost effective, at least from the long run. And what I do is when I teach my chemistry course in my class, I say, as a chemist, whatever you are doing, it should be explained to your mother-in-law, or you are not doing good science. So this is my concept of green chemistry to the eyes of my mother-in-law, and I should have given this as a title. So can we make a carbon-carbon bond without generating any waste or byproducts? Carbon plus carbon, carbon-carbon bond and no waste. Is it possible, or is it too idealistic? Well, a better question to ask, can we make a carbon-carbon bond in an environmentally friendly manner? Well, that will be the green chemistry equation, make byproducts that are environmentally friendly. Well, what are they? What about water, sodium chloride, oxygen that are already in the environment? Can we make those and it will be green? And the answer is yes. So the question is, how do you define waste? Because we don't always define what is waste. People will say, we have to eliminate waste. Well, before we can get rid of it, we need to know what it is, right? Let's take a step back and ask the question, what do we need to make a carbon-carbon bond? We need a carbon plus and a carbon minus. When carbon plus and carbon minus combines, you make a carbon-carbon bond. The green chemistry equation will be carbon plus, carbon minus, carbon-carbon bond, no waste. And that is green chemistry to the eyes of my mother-in-law. So the next logical question, where do we get our carbon plus and carbon minus? And they both come from baby carbon, or CH, or hydrocarbon. So life cycle of the baby carbon. So carbon plus is generated from a carbon X, where X is a good living group, and that leaves with a pair of electrons to make a carbon plus. Carbon minus, carbon X in turn comes from CH, or baby carbon, and X2. So every time you take CH and X2 makes CX, and you make 1 mole of waste. When you take CX and react with carbon minus, you make another mole of waste. So you make 2X minus per carbon-carbon bond. Carbon minus, on the other hand, is generated by deprotonation of CH by base. So carbon minus doesn't generate waste, carbon plus is the problem. So here is the baby carbon chemistry. CH reacts with X2 to make CX, carbon plus. CX gives up X minus, so you generate 2X minus as 2X. So C plus is the problem, C minus is not the problem. So every time you generate a carbon-carbon bond, you're generating 2 mole of X minus. So this is the bad guy, X. But is X the bad guy? Well, X plus 2 electron. So X at the carrier, electron carrier, electrons at the ultimate waste. So waste essentially is X minus 2 electrons with an electron carrier X. And what we do when you use a leaving group, we use a huge leaving group X. So we use 17, 18 atoms to carry a pair of electrons. It's like instead of a bicycle, we use a 18-wheeler to carry a 2 pair of electrons. So electrons at the ultimate waste. How do we get rid of waste? Electrons. Well, we can give it to either oxygen or chlorine plus. And so we need to find a partner atom that won't mind accepting the electrons, who like being negatively charged, and at the end of the day, make environmentally acceptable byproducts. For example, water or sodium chloride. So naturally, an environmentally acceptable solution will be electron can go to oxygen or chlorine plus, which is sodium hypochlorite, and gives you chloride minus, and that goes to sodium chloride and water. So this will be the green chemistry equation for the entire process. The electrons at the ultimate waste, X is the carrier, electron goes to oxygen or Cl plus, and that goes to sodium chloride and water in the ocean. So here is another example of finasteride synthesis, where finasteride is a long synthesis, and it's a very steppy synthesis, lot of waste. And I developed finasteride both for Merck and for Dr. Reddy's. And in Dr. Reddy's, we changed the synthesis to, so this is not a green process. And we use manganese dioxide oxidation. It's a very slow filtration. It's a very wasteful process. But Merck doesn't care, because Merck didn't have to worry about green chemistry. So a greener alternative is to use sodium periodate in the oxidation. Sodium periodate in presence of sodium hypochlorite, which gives you sodium chloride as a byproduct. And ruthenium is the electron transfer agent. It makes sodium chloride as the byproduct and no waste. So this was the synthetic sequence. So many steps got into one steps by this equation. So I'm going to go to the end of my talk, and yeah, let me just show this one. This is the general problem of catalysis. Whenever you have a carbon-carbon bond, this is a carbon minus, this is a carbon plus. When carbon-carbon bond is formed, you use a catalyst on the carbon minus end, for example, metal or catalyst, that is a coordinate covalent bond. But as this bond starts, this coordinate covalent bond becomes a covalent bond, and that ties up with the substrate. So coordinate covalent flirting is good, but when it ties up with the substrate, it's not catalytic. So what you do, you use something called silicon shuttle, where instead of a hydrogen, you use a silicon. And when this coordinate covalent bond becomes totally covalent, the silicon loves oxygen so much that the metal gets kicked out and the silicon comes to the oxygen. So this is how you break down a successful love triangle between the metal, the oxygen, using silicon as a silicon shuttle. So this is a general problem of catalysis, where you have to make catalytic. You have to use a partner that will take the catalyst out of the sphere. So I'm going to go to the end of my talk, because of the time limit. But so the bottom line is, every time I talked about green chemistry, I talked about cost. And every time I talked about cost, I showed you how cost is important. So environment and economy goes hand in hand. And without economy, environmental aspects won't work. So when I teach in my class, I say, God's book, this is the God's lab, this is our lab. And in God's book, you have two pages, the green page and the blue page, the green earth and the blue sky. And in man's book, you have hundreds of pages. So try to follow nature, try to follow the book written by God, and try to learn from nature to make the world a better place by simply looking outside the window. So green chemistry is not a fad or a movement or a process. Green chemistry is not a scientific discipline, a technique, or an aspiration. So the conclusion is that we can always do something ourselves a little bit. No one could make a greater mistake than he who did nothing because he could only do a little. So we say, you know, what can I do? A little bit. Well, we can always do a little bit, but combined, we can make the world a better place. And my solution is always look at nature and learn from nature and apply that to the lab. Thank you.
Yeah, any questions?
Yes, this is Eric. I have a I guess more. Let me just say that the talk was extremely interesting to me. One of the challenges that that is found typically in this current processing technology is that fixed bed reactors are inherently safer than anything that moves.
Yes.
So that is one of the challenges: reliability of the operation, safety in the operation, beat anything else, even if they are something that looks like a very attractive technology on paper, are conceptually safe, but once you want to implement it in a larger scale, particularly rotating equipment is something that nobody wants to have, because they break down, motors heat up. It is a challenge to implement. So implementation of these concepts is the most important challenge. So I'm not familiar with the pharmaceutical industry. So where do you see that? How can we remove that challenging situation? Because plant managers don't want to hear anything zooming or rotating or anything like that. So how can we go past that?
There are different variations of these. There are channel reactors, and there are fixed bed reactors. But the basic idea is that you don't need a big reactor. You can make channel or small. It's essentially a combination of reactors. So there's the engineering design that comes into the play. So in situations like this, you know, most of the time in Dr. Reddy's, what we are doing is essentially using flow reactors and flow processes, where most of the reactions we do, we always look at the engineer always works with the chemist in the lab. So when the chemist is running the reaction in the batch, because chemists don't like continuous processing because they don't think that way, but the engineers, they work together and say, I can manipulate that to make it a semi-continuous process. So by the time the process is developed in the batch, it's really ready to go to the next level. And we work parallelly to develop both batch and continuous processing. But a lot of the things comes from the engineering, and the designs are constantly changing, constantly evolving. So something that can be a problem today, you know, tomorrow there is a solution because somebody will come up with a better design for the system. But if one reactor doesn't work, we go to a different reactors. And in MIT now, they have developed with a continuous flow company where you essentially have a box where you can use plug and play. You can take, let's say you're doing a hydrogenation. You can take the hydrogenation box out and you can put a carbonylation box in. So inside a box, you can optimize the process. And it's a really neat apparatus. You know, it's like a little box like this size, and you have got 7 different plug and play module. So we can start optimizing in that scale. And then before we go, because you don't need to go to a big plant, you can pilot it in a small scale because it is semi-continuous. So if something breaks down, you just simply change that part which breaks down. So, but the designs are developing very, very quickly. And I don't know whether you have seen the Novartis process with MIT. That was just a phenomenal example of alizarin synthesis, all the way from starting material to tableting. And in probably a couple of hours, you're making tablets continuously. And I think that's the future of industry, because batch processing, you know, most of the time batch processing, we do it because that's how we teach chemistry in the classroom. But engineering and chemistry has to meld together to be the future. And in my opinion, flow chemistry is the future. But to understand flow chemistry, you have to understand kinetics. You need to understand the reaction from first principles. And every step, I mean, the example that I gave you is that, something that, that you are doing a simple chemistry where you can run a reaction and the starting material goes down and the product goes up, but the product, as it goes up, it comes down because it keeps reacting. So how do you solve that problem? Because you make a huge amount of waste, 60-65% yield. In a continuous process, it goes to 98-99% yield because it's out before the reaction is over, and it's a high temperature. So there are significant advantages, but it was not practiced that much because we don't teach chemistry that way in the classroom. Chemists are not taught engineering, and chemists need to learn engineering. That needs to be integrated.
I totally agree. Thank you.
Yeah, any more questions?